Hey, welcome back. So what we'll do as part of this lecture is take a look at the differences between a CPU and an FPGA, just so that you're aware of what you're dealing with when you're programming an FPGA. All right, so what we have on the screen here is the top view of two of the boards that I have. And well, one of them is the FPGA. So this is our SOANPAPDI board. Well, wow, what choice of color. Um, let's see. So this is the SOANPAPDI board, this is the FPGA, and then what we have on the right here, this is the STM32 discovery board, and this is a microcontroller. So I got to choose the right color here now. Okay, something bright, very nice. Okay, so FPGA and microcontroller, and let me just write like mu C here and FPGA. Okay, so the one on the right is called a microcontroller. A microcontroller is essentially a CPU with memory and peripherals. And in case of the SOANPAPDI board, the FPGA typically is a standalone entity, but it needs to find its configuration data from somewhere. So we have a memory here. So in terms of arrangement, the SOANPAPDI board is just FPGA and the memory, with the GPIOs being exposed out on the switches and the LEDs. And in this case, all of that memory, peripherals, all of those is contained within the microcontroller. And then through the pins, the UART comes out, some GPIO control block comes out, SPI comes out, and so on and so forth. Okay, so that's in terms of like physically or in terms of their composition. This is what they are. Again, surface level differences we haven't talked about. What really separates them. What you should notice is both in terms of like the physical look. They pretty much look the same. You know, uh, just by looking at a board, you wouldn't know whether it's FPGA or microcontroller or SoC. That has to do with the fact that circuits are typically packaged in such chips, and what's inside the chips, that's what counts. That's what makes for the real difference. Okay, so then what I'm going to do is I'm going to shrink this and put this on the side somewhere here. And so now let's talk about the differences in terms of like actually internal differences in terms of understanding them. Okay, so think about this. A CPU needs to be manufactured. And before it's manufactured, somebody needs to design it. And before even somebody designs it, somebody has to come up with an architecture. So then what matters to us is the following. So we have the CPU, we have the memory. And what we know about the CPU is a CPU is a solid state machine. Well, it's a solid state machine. I'll explain what that means. Okay. The fact that there are no moving parts in terms of like mechanical parts within the CPU, we call it solid state. The state machine part has to do with the fact that a CPU internally is just moving from one state to another. It could be, the fetch state, it could be the decode state, and I'll explain all of this. It could be like the execute state, and each of these states can have substates. Okay, now what does this mean? It means the following, that a CPU is a generic machine that can fetch, so it has internal circuits that can float or present an address to the address bus wires essentially. It can put some values on the wires, and those values or those bit values like zero, ones, and whatnot, that can reach the memory, and the memory then can send back or essentially put on the wire the data bus or the instruction bus. It can put the content on the given address, and that can come back to the CPU. That's number one. Now, the way the CPU is designed is going to read the memory and infer the, the value being read either to be an instruction or data. If it's an instruction, it will, so to speak, decode. So fetch is, going and getting stuff from the memory. The decode essentially means, okay, this is an instruction, now I need to do some action. So hopefully what you're catching on to is that a CPU it is inherently programmed to read through the memory, fetch the instruction, decode the instruction, understand what that instruction is, and then it will have different hardware components within it. For example, an adder, a subtractor, a multiplier, a floating multiplier, and whatnot. So CPU is supposed to then, select the right circuit, so to speak, the right part of the hardware, and then send the selected or the fetched data to perform that computation. So fetch instructions, fetch data, understand what the instruction was, act accordingly on the data. So all in all, a CPU is a generic machine that can read instructions, perform actions. Read instructions is the critical part. So if you were to add two numbers, you will need to keep those numbers somewhere in the memory first. And how they are placed, different story. Sometimes you can load them through external hardware. Sometimes, well, they just exist based on the previous computation. But whatever, let's assume that the numbers were present. And so there has to be an instruction somewhere which says, hey, add two number. But before adding, there have to be instructions above this add, which talks about fetching these two numbers inside the CPU's registers. So CPU internally has something called general purpose registers. It's a storage, if you will, very tiny storage. So there needs to be instructions on the top in something called the load store architecture, one of the architectures. This need not be always done, but the load store architecture uh, does what I'm explaining, which is it fetches the data first into the CPU internal registers and then acts upon that. So where am I heading with all of this? Well, even before you do addition of two numbers, there are going to be other instructions which need to set up the environment within the CPU for you to perform the addition. Okay, so if that is true, let me give you a real life example. So let's say we have the CPU and we have the memory here, and then there is some peripheral block. So let's say UART. So the UART then exposes two pins on the actual chip, which in our case, let's say, happens to be this. So this chip, somewhere there is a UART on one of these pins exposed. So that's the idea. So UART. And where are we headed with all of this? Just watch. So let's say I am to send two numbers, not A, let's say 1 and 2 on the UART. So externally, I'm going to type on some keyboard. As part of that, the 1 and 2 is going to appear here inside the UART. Now the CPU needs to execute a sequence which takes this 1 and 2 and let's say first save it in the memory. So, say read from UART, then write to memory. And then after that write to memory, it needs to fetch that data. And then let's say after it fetches, it needs to add them. And then after adding, it needs to write back to the memory. So the CPU is capable of executing these steps, a flow, a sequence of, these are just essentially instructions, right? Now my claim is that an FPGA essentially it doesn't follow a sequence. It in fact becomes one particular sequence, and you can only do so at the load time. Okay, so now let's talk briefly about FPGA. So in FPGA, my claim is it has internal components. So let me just draw them like so. So these are like building blocks, essential, components, and you have wires running between those. And then, okay, this is then the FPGA. And this is very critical. What I'm going to explain is very critical. And we have the memory. So now my claim is that these circles, or squares that circles that I'm converting to squares now, my claim is these are the basic building blocks. What these are, we'll talk about later. The name is LUT, lookup tables, or logical units. You can look this up. My claim is that these stay unconnected. They connect, let's say, on something like this. The idea is that they are not connected to each other just yet. And my claim is that in the memory, there is switching related information. You can imagine this to be, a grid of wires. And if I connect these two wires, then all of a sudden this connects to this. Let's just assume that. So in that sense, then you have building blocks that are unconnected, and the configuration in the memory dictates who connects to whom. That is number one. Now the difference then compared to a CPU is a CPU reads a memory to infer instructions, and FPGA reads the memory to set its own configuration. And now the interesting thing is a CPU reads instructions from the memory continuously. An FPGA will read the configuration only once. And now you can imagine, so as the FPGA boots up, it reads the configuration. These different blocks are connected to one another in a certain way. And now this entire thing becomes one circuit. And now to this circuit, you can also connect input and output. Okay, so now what happens? If you present the data here, so much like the UART example, if I were to send 1 and 2 here, what will happen is this circuit, the data will essentially flow, and as it flows, it will perform, or the output would be the addition. There would be no memory reads. I mean, the way CPU does it, there won't be any, oh, do I need to add this? Oh, do I need to fetch a number? No, none of that. As soon as the inputs become available, the addition is performed on the fly as part of a hardware circuit. So hopefully you're getting the hang of the fact that an FPGA becomes the circuit while a CPU is a circuit that is generic in the sense that it follows instruction to achieve an operation. All right, so why would you care to learn FPGA? Well, not that you should learn FPGA, it's more that FPGA is a vehicle for you to understand how hardware design is done. So the CPU, I talked about someone architected it, someone has to design it. So then the question is, how do you design a CPU? You design a state machine in something called HDL, hardware description languages. And you can then, we'll talk about this later in detail, but imagine that you have this circuit. Then the thing is, you have A, B, and C, let's say, and let's make it a little more complicated. So let's say we have this. HDL means you take this hardware circuit, and you describe it in a text format. We then say, hey, my inputs are, and there are like syntax to do this, Verilog, VHDL, those kind of languages. So you can then say my inputs are A, B, D, and my output is C, and my output is E. So E is just the output. This is, you know, well, this is an output as seen from here, but then it is also an input as seen here. So C then is input output, and these are just inputs. So, and then we also say, hey, C equals, A and B, and essentially, well, let's see. So E becomes, oh, well, wow, okay. Let me find my eraser. Okay, so E then becomes D ANDed with C, something like this, right? So we are essentially describing the circuit as text. Now what happens is there are tools which read this text and then convert it into something called, um, RTL, register transfer logic, or you can think of it as, transistor level connections. And this is like, a detailed topic in itself, but the idea is reading a text, translating into how different transistors need to be connected. And then whatever that final file is, that file can be sent out to fabrication labs like TSMC, Samsung, Intel, those guys, and they can then manufacture the chip for you. Now, someone architected a CPU, someone wrote the HDL for it, then that HDL was sent out to the fab, and then we got back the CPU. Now again, CPU is a generic machine. It reads from memory and performs different operations. Perfect, great. Now, between sending the CPUs, whatever, let's say the RTL to TSMC, the question is, can you check whether the hardware design you have created can essentially be, or rather, is that hardware doing the right thing? Is it, how do you debug? You can't send RTL to the fabs and wait like 6 months to get the chip back and be like, oops, this doesn't boot. This doesn't work as I thought it would. So one of the steps in between that you can do is you can take this description, this RTL, so to speak, and the RTL, what you can do is you can say, hey, let me put this on an FPGA. So what we are heading to is like an FPGA can become a CPU. A CPU cannot become an FPGA. So a FPGA, given that it has unconnected hardware units, you can be like, hey, let's do this. Let's take this RTL and let's see if, the same circuit, if realized by an FPGA, is that well behaved. I can run my tests on that. And once I'm convinced that, this hardware circuit is working as I'm expecting, I can send it to the fab. Now, one of the other questions is, when an FPGA can become a CPU, why not just use the FPGA? Well, the answer to that is an FPGA, recall, is not exactly transistor level connections of to realize this circuit. Sorry, it is more of some basic Lego blocks, some sort of a clay, so to speak, which you can connect together, and something that behaves same as the CPU state machine that you wrote in text form. This can become that. Doesn't mean that it has the performance of it. Doesn't mean that if this can be clocked at, let's say, 3 gigahertz, this can be clocked at 3 gigahertz. No, that's not correct. This can be clocked at maybe 12, because there are blocks here, the wiring is involved, the signals take more time to arrive at a certain point. This, that. Functionally, you can verify whether or not this circuit that you deployed is well behaved. But if you want performance, if you want that tied behavior of power, performance, and speed, well, then you got to take this description and send it to the fabs, TSMC, Samsung, Intel, uh, players of those nature, and then ask them to, at the transistor level, build this circuit for you, which has very few transistors compared to the same CPU deployed on an FPGA. So hopefully now I'm able to cement that idea again, that a FPGA is Lego blocks that you can, well, FPGA has Lego blocks that you can connect together using the memory, the configuration in the memory. So in this case of the CPU, this RTL will go in the memory, and then the FPGA reads that and rewires itself to become the CPU. In fact, you can design your own CPU and deploy it on an FPGA. A lot of people have done that. But hopefully I'm able to hammer home the point that FPGA is essentially Lego blocks that let you connect them to each other, the Lego blocks, and it so to speak realizes your circuit. So then the utility of learning FPGA is that, as I was mentioning, it's a vehicle to be able to design hardware circuits. So if you are someone who is, let's say, from the electrical engineering or electrical ECE, electronics and communications, let's say, and you want to go towards hardware design, well, being able to write in Verilog, being able to try out those circuits on FPGA, golden. And we should be able to do that. All right, so hopefully, I've managed to convince you to the fact that FPGA can become the hardware, digital hardware that you want it to be. There are certain limitations. So if your circuit is so complex that the number of building blocks within an FPGA are not enough, well, then you need a bigger FPGA. Bigger meaning not in terms of size, but in terms of the number of logical blocks that it has. So that is one limitation. The speed is another. FPGAs are great when it comes to processing inputs and, like, for example, image processing. You can receive an image, process it very rapidly and just give out the answer. Let's say converting colored image to black and white. A CPU will read like each pixel, perform the math on it, then write back a new pixel for the new image. An FPGA can simply look at the bit stream that's coming in, on the fly perform, like as the data flows, the colored image can get converted into black and white. It's very fast, even if the clock speed of the FPGA is like in megahertz. And a CPU, clocking away in gigahertz, sometimes FPGAs can beat CPUs in certain tasks. Anyway, so you can look up where all FPGAs are used in that case. Um, the final thing, much like how someone architected the CPU, well, someone has to architect the FPGA also. So people design the FPGA, check them whatever by using whatever primitive tools they had back in time, and then they said, okay, let's take this building blocks kind of a design and send it over to, again, the fabs, TSMC, Intel, Samsung, whatnot, and then have them send us back a chip, and this chip is the FPGA. So it's like you create a tool to create another tool. So FPGA is that someone designed. So in our case, then the FPGA we are using, well, that is designed by Lattice engineers, and it's manufactured by, they talk to TSMC and other fabs, get the chips, and they are the ones who are selling this in the market. One of the players we have, the once upon a time had Xilinx, acquired by AMD, Altera, also once upon a time acquired by Intel. So Altera, Xilinx, Lattice, I think Govin was another Renaissance, or there are many players in the FPGA field. We have chosen to go with, again, Lattice IS40 because it's very popular. There's a lot of open source toolchain and tools around it. The community is healthy, and that's why, well, again, we have chosen that. So hopefully I've convinced you again. FPGA, whatever code you write for it, becomes the circuit. It becomes the hardware. It's reconfiguring blocks, rewiring stuff to become that hardware circuit. A CPU, you don't write hardware stuff for it. You describe what instructions are to be used, what recipe to follow to achieve the task. So CPU follows, it's a solid state machine that follows instructions and achieves a result. And FPGA morphs itself to become the circuit, the digital circuit that you want. That's it. All right, so hopefully I have beaten the horse to death here. With this, I'll catch you in the next one.